what do I need to know to like be successful and ready to go in Algebra 1 or in pre-algebra, or really, I mean, any high school math class. And I know that we're getting to that point in the year where we're starting to, I mean, everybody's getting back, right? Like a lot of people I know have been back for like a week or so. I know many of my friends in Texas and some of the other places just went back today, but we don't go back in most schools in Michigan. We don't go back until the week of Labor Day. So we've still got another, I mean, really just another week or two. But I started going into my classroom this week, so that was something. It's always a little overwhelming. There's that there's that TikTok with David Rose from Schitt's Creek just like moving the chair. All right. That's kind of how you feel. It's just very overwhelming when you first get into your classroom. But persevere. Every teacher knows that like you're going to get there eventually, and whatever it's like the first day of school, that's what you get. That's kind of where you are. And like with I think elementary, it's probably a bit more of like you need to have everything like perfect and ready to go. I don't know for sure because I've never been an elementary school teacher, except that one year that I taught PE. That's a story for another day. With middle school and high school, you get a little bit, it's a little bit squishier. You know, the kids are okay if you're still like changing and getting things adjusted. But that being said, I really put a lot of pressure on myself to get everything all done before the first day of school. So if you guys have any questions, if you guys have any problems, any concepts, anything like that that you need help with, or that you want to talk about, or anything like that, stick it in the chat, and I will do my best, and we can work through it. You know, a lot of this is kind of puzzling through different things in the different concepts and things like that. If there's anything that you're just kind of curious about or never really made sense to you, let's get into it. Unit circle. Okay, that is a really good, I'm going to jot that. How do I explain to fifth graders why when subtracting a negative integer you add? Okay, this is a really good kind of concept, because you're right. Like when you say you're subtracting, right, you go to the left. But then when you're subtracting a negative, it goes, oh, well, then we're actually going to the right, right? So you can go through and you can talk about like, you know, like, well, when it's a negative, that flips the direction, right? So if it's minus a negative, right, the negative flips the direction. So where you would go left to minus, it gets very confusing when you're trying to just have, especially like fifth graders. I have a fifth grader. Well, she's now a sixth grader, but I have a fifth grader. Like trying to memorize those rules, it's going to be really difficult for a lot of kids because it's not intuitive. So what I try to say in my language, and this is like when I taught middle school math, when I would teach them the negatives and the positives and adding and subtracting, what I would try to do is, if you see an addition sign, that's making it more of something. So like 2 plus 3. So you're taking 2 and you're making it more 3 by 3, right? Making it more of 3, making it more of positive 3. So if adding is making it more of something, subtracting it is making it less, right? So 2 minus 3 is making it less positive, right? So this is making it more positive 3. This is making it less positive. And that also gets them into the idea that like these numbers have like kind of similar things. So you can think of this as being less positive, like the reverse of the reverse is positive. Yeah, something like that sort of. So like, but I really talk about like if you're saying plus negative 3 or you're saying minus negative 3, what I always say to my students is you're making it less negative, right? So if I have 2 minus 3, I'm making it less negative, right? So less negative would be more positive. So that's why it's 2 plus 3, right? So if there's a kid that's really struggling, or if you're really struggling with this whole like, okay, do I go right? Do I go left? That getting into that like memorization piece is something I try to stay away from. Some kids are going to get it, right? They memorize the rule, they got it, but they may not fully understand the conceptual of why. Other kids are not going to get the rote memorization that this is just addition without that conceptual piece behind it. And so when you're looking at this, if you have the less negative, right? Or you can look at it as making it more negative or more positive, right? So looking at that usually can help those kids start to click with it. Because honestly, the number line sometimes doesn't make sense. Sometimes a lot of students have trouble, especially in 5th grade. I still have a number line in my high school classroom, and I use it all the time when we're talking about absolute value, when we're talking about vectors of motion, when we're talking about all these different things. I still use a number line, and I'm telling you that some kids don't fully understand a number line until they're in high school. That's like my hot take right now, is that some kids don't even understand a number line until they get to high school. It just happens. It's that number sense and kind of getting a feeling for it. A lot of times what may work is some manipulatives, right? So some manipulatives when you have like the positives and the negatives. I don't have any, I don't really have anything here, but I was just working with a student who is actually going into high school, and just the negatives, the integers just really weren't clicking with him until I started getting out the manipulatives, right? So you could think about, well, I mean, I guess I can draw it out. So using manipulatives, but for state testing, they can't use them. Right. Totally get it. Manipulatives are really useful for understanding things in the beginning, but really the ultimate goal is for students to start being able to visualize the manipulatives in their head. So that's why we use all of these different boards, all these different things, these different drawings and things like that, for them to then understand, oh, that's why it's addition, right? So let me show you what I mean. So let's go to like 2 minus -3. Now, I had a really hard time with this when I first started teaching because I didn't understand really how to like show this with manipulatives. I can't get these open. Okay, so I'm gonna get some different color dice to show them here while we're, thank you. Okay, this is Tenzi. By the way, this is such a great game to have in your classroom because, I mean, there's a lot of, you guys know that like I love my dice, but also there's so many different games that you can play with this. It comes with a whole list of games that you can play, but it's also just a really nice, they're nice dice. I like these, the colors. So I'm gonna use, let's do the reds are negatives and we'll do the blues are positive. Okay, so I'm gonna turn these all to be 1. Ooh, Quicks. QWIXX. Put it on the list.
Am I supposed to be picking this list?
Yes. That's part of your job. Okay.
Meanwhile, I'm going down like, oh, we need some HDMI connectors.
Different priorities. Okay. So when you're looking at these, so again, if you've got a student who's really struggling with keeping these straight, you know, there's a lot of different, there's so many different ways that you can teach the relationship between integers. And again, if a student doesn't have a solid foundation with this, it's going to be really hard for them to go through algebra because there's so much that we talk about that is like where we talk about like canceling out and getting rid of these things, right? Keeping it in balance. So ultimately, you've got to understand that like if I have a positive 5 on here, I can't just take away that positive 5, right? I need to put a -5 there so they cancel out, but I also have to put the -5 over here. Okay, so those are things that you've got to really understand. So we've got the positives. I know this is trying to make all of these say 1 so we don't get too confused. Okay, but ultimately it's the blues are the positives and the reds are the negatives. So the number 1, and you can honestly use any sort of ideas or any sort of manipulatives. You know, I've got some discs in my room that are like 2-sided little counter tokens, right? You can use anything. You can use coins, you can use like flashcards, Post-its, whatever, right? But ultimately, the big thing to understand is that 1 negative, 1 positive, that's 0. So I could put as many here as I want to, right? But that's 0 because you have +1, -1. If I give you $1 and then I take that dollar away, you're still at 0. So now, if I've got +2, and I need to, well, let's start pretty simple, right? So let's just start with 2 minus 3, okay? Now also when you're doing this, you would look at like, you know, what are these different numbers, right? So if I had, I know I'm kind of jumping all over the place, but so if I had this here, right, what number would this represent? Well, I've got 2 positives, but I've got 4 negatives. So these are going to cancel out. I'm just left with -2, right? So that's kind of the first, yes, 0 pairs. Thank you, Kim. 0 pairs, okay? So if I have +2 and I need to take away 3, okay? So what I need to do is I don't have 3 so there's 2 different ways you can go over this, but we'll do both ways, right? But if I'm just going to take away 3, I don't have 3 to take away, right? But if I put in these 0 pairs, now I have 3 to take away. And then I look at those 2 canceling out, and what I'm left with is 1 negative. So it's -1, okay? So that's one way to show it, right? Another way that you could show it is, if you start with 2, right? You can just put in one of those 0 pairs because now you have 3 positives to take away. You're left with -1. But what you can also do is this is a good time for you to say, like, well, it's kind of hard to do that. If you can also explain that this is the same thing, and this is sometimes a jump that they're ready to make, but sometimes they're not. And you can just show that to them, and if you see that look on their face and you go, never mind, let's try another one, right? So if you have that -3, you can say, well, it's also the same thing as just adding -3 because look, I'm still left with the same thing. I'm still left with that -1, okay? So now, if we have that 2 minus -3, okay? So I'm still starting with +2. Now I need to take away -3. So it's the same thing, right? When we're taking away, we need to start adding in those 0 pairs, right? So we're going to take away -3. So I can't just add in 3 negatives to take away, right? But what I can add in are 3 0 pairs. So if I put in 3 0 pairs like this, that's still +2. I haven't changed anything about it. That's still +2, but now I have 3 negatives to take away. So that's +5. If you do this a few times with students, they will usually make that jump to be like, oh, wait, so it's the same thing as adding. It's like, there it is. That's it. 2 minus -3, it's less negative, which means it's positive, which means you're adding, right? It's helping them realize that there are so many different ways to look at something, and if you put emphasis on them just memorizing the algorithm, the algorithm will work, but they may struggle to understand how to apply it in a new context. Meaning, they may not realize that it still applies to fractions or decimals or things like that when they start kind of, when they just memorize it, they're like, oh, well, that you just put the 2 lines, you take the 2 lines and you make them into a plus and it's add, done. But the concept isn't there. They just know how to solve that problem. They're not doing math, right? And that's a big difference. Solving problems is not doing math. It's math up. That's going to be my hot take. Solving problems is not the same thing as doing math. It's great. Helpful, but it.
Give me a tight top for that. Give me a hook. Give me a hook.
Is doing math just solving problems? Nope.
Sell it right to the camera.
Is doing math solving problems? Nope. Those of you who are here, exactly. They will also try to apply the algorithm somewhere else, like when they're multiplying. Exactly. Because they don't get what they're doing. They know how to do it, but they don't understand what they are doing. That's such a huge difference in the classroom. When you would get those mad minutes and like memorizing the multiplication tables and all that kind of stuff. Those are helpful things to memorize the multiplication tables, but also like understanding that 2 times 3, and somebody earlier had talked about like how to get the multiplication. So starting by reminding them that multiplication is just repeated addition, right? 2 times 3 is 2 plus 3. No. It's 2 plus 2 plus 2. 3 times. Whoopsie. But so teach the concept first. Let them pick up on the pattern. Let them start feeling like they're discovering it on their own. Yep. So if they just memorize the algorithm, they're going to be thrown off if it's a problem they've never seen before. Right? I get that all the time where the students get on, well, I don't get it as much anymore because I've stopped doing this, but they, all of a sudden on the test, when you try to just, let's see if they can apply this. If they've just memorized the algorithm, or if you've given them the same problems over and over and over, and then you give them something new, they can't do it. And the reason is because they have memorized the rule, they have memorized the algorithm, and if it doesn't look exactly alike, they can't do it. For example, if you're adding 2 fractions, right? So I just did this with a student the other day. We have been working on fractions for months, like adding, subtracting, multiplying, dividing. She can do it. Boom, 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 boom. So we went through and we did our warm up. We were doing all of our fraction stuff, just rehearsing, right? And then I said, okay, what about 1/2 plus 2/3 minus 1/4? And just that jump of 2 to 3 fractions, I had to talk her through it a little bit because it's not the same thing that we've been doing for months and months and months. It's just that little tiny change, right? Or, you go through all the integer rules and all of a sudden you throw a fraction or you throw a decimal in there and they're not going to get it, right? They don't realize because they've just memorized exactly what they can do, right? What they do when the problem looks like this, right? It's just sort of like a game of memory, right? The flipping over the cards. Like, oh, if it looks like this, I do this. If it looks like this, I do this, right? But if they understand the why, they understand what they're doing, they can do this, right? And so you're just still looking at, okay, you're just adding or subtracting fractions, common multiple, or common denominator, you can multiply them all together, totally fine, right? You could do 12, you can do whatever, right? And then once you get all of the numerators sorted out, you can then, it's just adding and subtracting, right? It's nothing brand new. It's just applying it in a little bit different way. And that's That is doing math, right? That's doing math, is puzzling through and figuring things out. What is it? Problem solving is what we do when we don't know what to do. Just look for something familiar, right? That's what I always tell my students and my friends and my colleagues. Just like, what can you do with this, right? What's familiar? What do you know how to do? And then go from there, just keep putting one foot in front of the other.
You've gotten a couple of nice comments on your other videos.
Oh, nice.
One was from Polly, and she said, I nearly failed every math class I ever took until 10th grade. I was at the grocery store and saw 3 pounds for 99 cents. It clicked. 3x equals 99. X equals 33.
Oh.
I ended up passing calculus. I'm a math person.
Yes. I love, and like some people that are probably in this chat right now, it's just now clicking for you. That's fine. It may not fully be clicking for you. That's fine. For me, I was a bit of a late bloomer. Like I had a hard time with math in middle school and high school. And then it finally kind of clicked for me, really like my senior year in high school. That's when it really clicked for me. Because sometimes our brains just aren't ready for it. You can be showing your students, or you can be shown as a student, 15 million times how to solve an equation. And then one day it may just click.
There was a question too.
Yes.
Willis. I'm a newish math teacher, and one of my classes...
Yay! Welcome to being a math teacher!
One of my classes is struggling to understand product and quotient exponent rules. I try to make it super simple. Every other class catches on fine. Any suggestions?
Okay.
Could you please repeat the question?
Yes. So, here's the thing about exponents. There's really only I don't know, really, I almost want to say there's really only one major thing you have to remember about exponents. Remember, we don't want to just memorize the rule, right? Oh, it's product of a product, and product of a quotient, and product of a power. No. You look at the exponential form, and you look at the expanded form. Go from there. So, if I have x cubed, that's the exponential form, x times x times x. Kim, I think you and I are like kindred spirits. Every time I look at the chat and you're writing stuff in there, I'm like, yes, that's exactly where I'm going. I love it. Okay? So x cubed is x times x times x. Great. We've got expanded form. We've got exponential form. If you can do that, you never have to memorize a single exponent rule. Because here's the thing. Let's say, okay, I've got x squared times x cubed, right? So x squared times x cubed. Now there is a rule, right? There are exponent rules where, if you do this, you add the exponents. If you do this, you multiply the exponents. If you do this, you subtract the exponents. You don't have to memorize anything. You don't have to memorize anything, okay? Thank you, okay? All you have to memorize is just this expanded and exponential form. Because if you know this, you can figure out this. Easy. X squared is x times x. X cubed is x times x times x. So what is this? X to the fifth. Done. I didn't have to memorize a silly rule. Silly, sure. Okay. Yeah. 19-year math teacher here. Okay. If I had, the other one is x squared, cubed. So this is power of a power. This is the product rule, I think. Product of a power, product power rule, something like that. See, I don't even know what they're called because I don't want to memorize them. Okay, but I have x squared to the cubed, right? So what that is whatever's here, I'm going to cube it. So I have x squared times x squared times x squared. And now I've got x times x times x times x times x times x. It's x to the 6th. Done, okay? So here you can see the rule, right? The rule is that here you add them, here you multiply them. But did you have to memorize them? No, you can just figure it out, right? You will eventually, if you are working with this enough, you will eventually get there. That you'll probably like start to kind of like, oh yeah, I add them. But I even find myself when I'm teaching this, I usually have to kind of remember and double check because it's silly. Like, right, you add them, yeah. But if I just see that on my own, I have to always visualize this. Like my brain goes back to this. And then I remember, right, you multiply. Correct, okay? So then the quotient rule, again, you just have to do this, expanded form, okay? All right, I love exponents. Okay, so now if I have x cubed over x squared, what do? Ooh, I'll get to negative exponents in just a minute. Because that one is just like a one and done. X cubed over x squared. We expand, right, in expanded form. So I have x times x times x over x times x. Now, this one is going back to basic fraction things, right? Where you've got x over x, that's 1, cancel. X over x, that's 1, canceled. All I'm left with is x. So the quotient rule is technically you subtract the exponents. Okay, but you can also think of this as canceling out. This actually makes it a lot easier when you have a whole lot of, This makes it a lot easier when you have a whole bunch of different variables. Because remember, these only apply when the variables are the same, right? When just those x's, right? If there were y's in here, like the y would only cancel with the y and all of that kind of stuff. Negative exponents. This is a really fun investigation. Have you ever wondered what a negative exponent does? Let's get into it. So with a negative exponent, what I like to do is, again, what is math all based on? It's all patterns, right? It's all patterns. So let's check this out. I'm trying to pick the right colors. Let's go green. Okay. So 2 squared is 4. 2 to the 1 power is 2. Okay. This is usually one of like the very first things that I talk about when we talk about exponents. Okay. So 2 squared is 4. 2 to the 1 power is 2. And sometimes I have my students like doing that on calculators. Great. And then I say, okay, well then what's 2 to the 0 power? Sometimes they know. Sometimes they do on their calculator. Sometimes they don't know. And I say, well, it's 1. Anything to the 0 power is 1. Just like anything over itself is 1. Right? So then we start talking about what is 2 to the negative 1? Okay? And we start looking at patterns. It's all patterns. It's all patterns. Okay. So here, this pattern here, what do you notice? I'm doing this like my lesson. Okay. So what do you notice about the exponents? We're going 2 to 1, 1 to 0, negative 1. So this is minus 1, minus 1, minus 1, right? We're subtracting 1 from the exponents each time. So for each step, when I subtract 1 from the exponent, I divide by 2. Same thing here. I divide by 2. It's not going to change. The pattern doesn't change. Just because it's going into negatives, it's a pattern. It doesn't change. So same thing when I subtract 1 from the exponent, you divide by 2. So what is that? What is 1 divided by 2? It is 1/2. So then a 2 to the negative 2, well, I subtracted 1, I divide by 2, 1/2 divided by 2 is 1/4. Again, the pattern never changes. So minus 1, divide by 2. The pattern's never going to change. So what does a negative exponent mean? It means it goes on the bottom. That's it. That's it. Negative exponent, it drops down. That's what the negative sign does. So we could be writing these here. I could have this as 1 over 2 to the 1. This could be 1 over 2 to the 2. Because once you drop that number down to the bottom, the negative goes away. That's it. Yeah. I mean, that's mapped up. That's it. That's all it is. But if you just tell them like, oh, well, negative exponents just mean that they drop down to the bottom. If they don't understand the why, if they forget the rule, they're screwed. If you're just memorizing rules and then you forget the rule or you get it mixed up with something and you don't know where the rule came from, how are you going to figure it out on the SAT or on a standardized test, right? If you're just memorizing the algorithm and you see a new type of problem, you see a new, like a new situation, right? You see a negative exponent, you go, what? What is that? And then what's really fun is when you get into into rational exponents. But that goes into like roots and radicals and things like that. Oh my gosh, I can't believe it's already 8:45. You can always get the rule back with the why. Yeah, exactly. Like you can always go back and figure it out. And that's what I always emphasize with my students is like, you can memorize the rule, that's fine. But you have to understand where the rule comes from in order to get that piece, right? You have to understand what it means, right? I know time flies. These lives always go by really fast. Okay. Yes. So here's one of my favorite things. Oh my gosh. My students always get so, I think embarrassed, I guess would be the right word. Which would be factoring polynomials. I love factoring polynomials because it's just a puzzle. I mean, math is all just solving a puzzle, but factoring polynomials is like a super fun, challenging puzzle. So let's get into it. So factoring is, this is a very like nuanced definition. So factoring, it comes from division, okay? But really when you're talking about like, let's 63, okay? If I have 63 and I'm gonna factor it, I have 9 and 7, right? I have 3 and 21, right? These are all factors down here, right? So it's kind of like dividing, right? Like I would figure out the factors by division, but you're just writing it as like you're writing it as the product of those two things, right? And we're doing this all the time, like when we're solving equations and things like that. But so factoring polynomials, this is I'm primarily going to focus on like quadratic polynomials, right? So anybody going into, especially like Algebra 2, Trig, Pre-Calc, maybe Algebra 1 honors or something like that, you're going to need this. So factoring polynomials is just, again, if I told you to factor 21, right? We start doing this in lower school, right? Or in elementary school. Factor 21. Okay, well, I know that 21 is divisible by 3 and 7. So again, this is where that times table comes in handy. And this is the lesson why I still have a times table on my walls in a high school classroom, is because you need to see where is 21, where is 24, where is 36? What are all the different factors that go into making this? What are all the different ways that I can multiply, or all the different numbers I can multiply to get this value, right? So 3 and 7 are the factors of 21. Okay? That's the opener, right? I factor this because I know that these two multiplied together make that. Ultimately, you know that you have factored it correctly if when I multiply these together, I get my original thing. Okay? So, I'm going to flip this, turn this board this way. Need some more space. All right. So if I have something and I say factor x squared plus 7x plus 12. You know what? Actually, I'm going to go backwards on this. If I multiply x plus 3 times x plus 4. Okay, I've got two binomials. If I multiply those together, right, then I can use my FOIL acronym, right? So I can use FOIL. So that means first, so I multiply the two first terms together, which is x times x, which is x squared. Outside is x times 4, which is 4x. Inside, which is 3x. And the last terms, which is 3 times 4, which is 12. If I combine my like terms, then I have x squared plus 7x plus 12. Okay, so if I have this and I said factor it, right, or write it in the factored form, what I would be working towards is this. Because, again, we go back to like 21 is 7 times 3, right? We go back to x plus 3 times x plus 4 is x squared plus 7x plus 12, okay? So we look at, these are the factors because if I multiply these together, I get this, okay? So now how do we get there, right? How do we get to this point? So let's look at another example. If I have... Let's start from the beginning, right? We have x squared plus, we have x squared, hi Gma Barb, x squared plus, let's do 5x plus 6, okay? So I'm going to say factor this. So I'm trying to figure out and think back to like how they were set up, right? There were two binomials that were multiplying together, right? So we know that two binomials multiplied together gives you something in this form, okay? We're not going to get into difference of squares and all that right now. So don't come at me in the comments. But we're looking for two binomials that when you multiply them together, you get this. Just like with 21, we were looking for two numbers that you multiply together to get 21. It's 7 and 3. So when we're looking at this, the way this works is if we have okay, this here is going to be like the result of multiplying those two numbers together, right? So we're looking for two numbers that multiply to equal 6 and add to 5, right? So multiply to 6 and add to 5. So if we think about 6 and we kind of go over here and I go, okay, well, it's 1 and 6 and it's 3. Well, 1 and 6 add to 7. 2 and 3 add to 5. Those are my numbers. So my two numbers are x plus 2 and x plus 3. So they just go right there. That's it. That's mathed up. Gets a little tricky sometimes when you're talking about negatives, but it's not so bad. Not so bad at all, okay? But so we've got the plus 2 plus 3 because this is positive and this is positive. So 2 times 3 gives me 6. 2 plus 3 gives me 5. Okay, and I can double check that by foiling these together, right? So if I foiled these together, I'd get x squared plus 3x plus 2x plus 6, okay? All right, so now if there's a negative in there, let's do x squared plus 4x minus 45. Okay. So since I know that it's going to be these two binomials, right? Okay. Now this method that I'm showing right now only works if this number is 1, right? If there's no coefficient in front of the x squared. We'll get into if it's a non-1 in a minute. Okay. So here, if you notice, I've got a negative sign. Ooh. So what that means is that negative means that these two signs are different. That means that one is going to be positive and one is going to be negative. Because if I take a positive times a negative, they're going to be a negative number. So now what I'm looking for is two numbers that multiply, so the rule doesn't change, right? Multiply to negative 45, that's multiply, and add to positive 4. So negative 45, let's see, I know I've got 1 and 45, right? I don't have 2, I have 3 and 15, right? But I can't really get those to equal 4, right? So that I could do 5 and 9. Ooh, if this is positive 9 and negative 5, that would give me positive 4, right? So I've got positive 9 and negative 5, right? So I put in my numbers, x plus 9 and x minus 5. It's mapped up. And that's all it is. Multiply, multiply, multiply. Okay? All right. So now, factoring polynomials, there's actually a ton of different ways of doing these, which is, I think, one reason why I like them so much is that there's lots of different ways to think about them. So there are lots of different ways to do these, and especially when you get into the polynomials where the front number is more than 1. Should we get into that or simplifying radicals? What do you think? Should we do more factoring or simplifying radicals? What do you guys think?
Yeah, I would talk to your chat. There's some people asking, they've got a certification coming up. There's someone, Curious Joe, says, I have ADHD and can't seem to put it all together to understand discrete mathematics. Any suggestion? An effing idiot is doing his best, or their best. Unclear on pronouns.
We're all doing our best.
Am I?
You are. You're doing like 15 different things over there.
Yeah, it's true. I know I'm killing it.
As far as ADHD goes, it's you just kind of have to keep working at it and seeing which methods and things work best for you, and lots of different ways of thinking about things. And the nice thing about kids these days is that there are so many different videos and ways to look at things, and there are more and more videos coming out about like upper level maths that are making it clearer to or like making the more advanced maths, like it's starting to give a lot of different ways of doing those things. There's still a lot of stuff like with calculus that it's just like, this is just how you do it. So, oh, my calculator. This is called a NumWorks calculator. NumWorks. It's a really neat calculator. It's kind of hard to see on the screen. It's not going to adjust the it's not an autofocus. But this is a really it's a much more intuitive calculator with the TI-84, 83, whatever, the standard, right? I think Sarah Silverman had a thing about like the Texas Instruments had bamboozled an entire generation to buying these calculators, which is true. But it's also like, this is the exact calculator that my parents bought for me when I was in high school, so it is a workhorse. But the NumWorks calculator it's just a lot more intuitive. It has a lot more different like menus. It's about the same price. Now, the only thing that I have found personally is just it's a little bit of a learning curve because I'm so used to the TI-83. But there are things like, for example, here, I know it's really hard to see, but so one of the things that I was wanting to talk about Next was actually something with simplifying radicals, which is like if you take square root of 27, right? And if you put it in your calculator, you do square root of 27 and I get 5.196152423. Well, that doesn't help me, right? This is a radical, it's an irrational number. Like that doesn't really help me except unless I'm trying to estimate, right? And I say like, it's about 5.2, sure, okay? But when you're working with radicals, this square root of 27, an acceptable answer for that is not 5.2 or approximately 5.2, right? Simplifying radicals, again, there are just a few things that you have to remember about them. So 27, if you think about the factors, it's all back to factors, right? But 27 is the set, let's see, so 27 is 1 and 27, and it's also 3 and 9, and that's it, right? When you're simplifying radicals, you want to look for the perfect squares, right? So I can't take the square root of 27 because you saw in my calculator, it's 5.196152423. You don't want that. But I see that there is 9, and I can take the square root of 9. It's 3. So square roots are just roots, right? So the square root of 27 is the same thing as the square root of 9 times 3. Now, if I have this root symbol, this radical symbol, it's over the 9 and the 3, I can actually split these up. It's the same thing as root 9 times root 3. So the root of 9, the square root of 9, 3. Square root of 3, again, it's an irrational number. Square root of 3 is the square root of 3. I don't know what it is, right? But if I simplify this, I would write this is the same thing as 3 square root 3. Square root of 9 is 3.
I was trying to zoom in for you.
So the square root of 9 is 3. It's this 3 right here. I know when I have multiple 3s, it gets a little bit funky. But so this square root of 9 becomes this 3. And this 3 is this 3. Okay. Yeah, and this does make it easier because then you can treat this root 3 as like sort of like a variable. Like if I had 3 root 3 plus 2 root 3, it's 5 root 3, right? So it makes it a little bit easier to work with. Now, that whole discussion, which I did actually have it on my list to talk about, was simplifying radicals because I do like doing that, is to also show, like on my calculator, you really can't see this, can you?
Well,
but so on this calculator, on the NumWorks calculator, so I put in square root 27, and it gives me 3 root 3. Can we zoom in?
Well, we can zoom in. Hold on.
But I don't know about
zoom in, and then watch this. Watch this, everybody. Huh? Are you ready? Oh.
There. Oh.
Did you do it or did I do it? You must have.
Oh, I did. Oh, you know what? It's starting to go to sleep.
Okay.
But maybe you can see it.
Yeah, but the sleepy.
So this calculator does give you that 3 root 3, right?
Hard to see it live, but the record will crack your guys.
So like there are things on this calculator that are really amazing. It'll give you it'll kind of do the same thing sort of with fractions and things like that, where it'll give you the simplified fraction. It'll give you all this other information about the numbers. And it's about the same price. I think even maybe a little bit. I think it's like $99. And the graphing capabilities are really good. But again, it's a pretty new calculator. They sent them out to a lot of different teachers, which I think was great. But I'm definitely like kind of forcing myself to use this one more frequently, and I'm finding it to be really nice, especially for kind of making that point of like, no, square root of 27 is 3 square root 3, If you had told me in high school I'd be drinking and watching math live streams for fun, I'd pass away. If you had told me in high school that I was going to be a math teacher, I would have passed away. Yeah, it's what an interesting pathway, right? An interesting path to get here, but we're all here now. Anything else that I might have missed? It's 9:07.
You can keep going. Like, literally, now it's all on you. Like, they just like it when you go more than an hour, but if you're feeling it, you're feeling yourself.
Well, we have done more than an hour, right?
Well, you remember we had about a 7-minute restart.
Oh, did we? It was that one? Oh, interesting. Okay. Here's some, what is it, a $5 word or whatever it is? Like a $10 word, rationalizing the denominator?
Sure.
How to rationalize the denominator, because I've kind of been saying this a lot, that the roots are irrational numbers, right? So a math no-no is having a radical in the denominator. So for example, this, right? If I had square root of 5 over square root of 3. Oh, I just got the little like inactivity thing. There we go. So square root of 5 over square root of 3. So I cannot simplify these radicals anymore, but there is a big problem. Boop, 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 boop. Why is it a no-no? Because I don't care. I bet there is a really good reason, but the way that I kind of explain it is it's sort of like you want to simplify all the terms, right? You would combine all the like terms in something. You would simplify a fraction. You would not have a rational, or you would not have a radical in the denominator. I'm sure there is a better mathematical reason. There's got to be. But it's a no-no. So, and it is kind of fun to get rid of it anyway. Okay. So what I do is, since I can't have that radical, right? But so if you have, square root of x times the square root of x equals x, right? Square root of 9 times the square root of 9. Square root of 9 is 3. Square root of 9 is 3. Bye, effing idiot. I don't like your username. 3 times 3 is 9, okay? So if you multiply these, they're the same variable under the same root. It just kind of like makes the root go away, right? Because square root of x is just x. Square root of 9, 9, okay? So what I would do with this is I need to get rid of that root 3, okay? I can always multiply by a version of 1, okay? When you get into upper levels of maths, you're going to need to remember that you can always multiply by 1. So I'm going to multiply by a version of 1 that helps me accomplish something. And in this case, that version of 1 is square root of 3 over square root of 3. Why am I doing that? I'm doing that right here to get rid of that radical underneath. So square root of 3 times square root of 3 is 3, right? So now what I've got is I've got the square root of 5 times the square root of 3 over 3, okay? Square root of 5 times square root of 3 is square root of 15, right? Because we can loop these under the same little radical sign. So then 5 times 3 becomes 15. So this is root 15 over 3. And that's mathed up. Okay. I think I'm done.
Okay.
That was a good Mathursday.
It was a great Mathursday.
Great Mathursday.
Why don't you end the stream and we'll do a couple of your little housekeeping things. And, yeah.
All right, guys. Thanks for joining me on Mathursday.
Hey, thanks for 100,000.
Thanks for 100,000. 100,000 followers. That is gabunkers. Who would have thought? Not us. What is it? What is it from Paul Rudd? What is it?
Look at us.
Look at us.
Who
would have thought?
I had an idea.
You had an idea. You knew. All right. Okay, guys. Have a great night. Love you all. Keep mathing.